Question 4 is about the photoelectric effect. And we can tell that because it says it's about the photoelectric effect. And as soon as we know we're dealing with the photoelectric effect, it's probably worth digging out the photoelectric effect equation, which you hopefully will remember, but it is on the data sheet. HF equals phi plus EK max. So I'm just going to jot that down here. HF equals phi plus EK max. And we'll look at this equation. We'll remember what the photoelectric effect is. We say that a photon of light hits an electron, gives its energy to that electron, and if the electron is given enough energy, it's able to escape from the surface. So HF is the energy which the photon has. Phi, of course, is called the work function. That's how much energy the electron needs to be given in order to leave the surface. And that applies to the electrons which are the easiest ones to get away from the surface. Other electrons might need more than that, but that's the minimum amount needed. And EK max, well, that's what's left over, because that's how much energy the photon provides. That's how much energy the electron needs to get away. So this is what's left over. And what's left over will be in the form of kinetic energy of the electron. So the first part of the question, what's the effect of increasing the frequency of the light? Now a few people seem to get a little bit confused, because some people seem to think that the frequency of the light meant that there were more photons. And I can sort of understand how you think that, because frequency does mean how often things happen. So you talk about the frequency of the buses, how many buses arrive in a certain time. Why isn't frequency of the light how many photons arrive at a different time? Well, we have to remember that there are two ways of thinking about light. We can either think of it as a wave, or we can think about it as photons. If we're thinking about it as a wave, then the wave has frequency. If we think about it as photons, the photons have energy. And when we put F into this equation, H times F tells us the energy of the photon, and the F that goes in that equation is nothing to do with how many photons there are. It's to do with what's the frequency of the wave that the same light would behave as if we were thinking of it as a wave. So what can we say? If you increase the frequency, if F gets bigger, HF gets bigger. So that means that every photon that comes in has more energy. And that means that every electron that is hit is given more energy. Well, the work function is not going to change. So what does change? EK max changes. So if you increase the frequency of the light, the maximum kinetic energy of the electrons will increase. The electrons that escape from the surface won't all have the maximum value of energy, but they will be spread out over a bigger range, up to a greater maximum. So if you state the effect, the maximum kinetic energy of the emitted electrons, or we could just write the photoelectrons if you wanted, increases. And because the maximum increases, it means that the sort of range over which because the maximum increases, it actually means that the average kinetic energy also increases. And if you missed out the word maximum, you said the kinetic energy increases, that would have been okay. So we've stated what happens. We haven't explained. Why does it happen? Because each photon has more energy to give to the electron it collides with. Or you could refer to the equation, use the equation to show that EK max have to increase. That'll be okay as well. The second part, what's the effect of increasing the intensity of the light? Now the intensity of the light means how bright it is. It means how much energy there is every second. So if the energy is carried by photons and you're getting more energy every second, the frequency of the light isn't changing, it's still the same colour light. So we're not changing how much energy each photon's got. The photons are the same as they were before, but we're getting more energy, so there must be more photons. So more photons hit the metal every second, and that will cause more electrons to be emitted every second. So the effect is more electrons are emitted every second, and the reason because more photons hit the surface every second. Part B, the wave model was once an accepted explanation of the nature of light. It was rejected when validated evidence was used to support a particle model of the nature of light. I don't think that's quite true. I don't think we reject the wave model. We still use it sometimes. We just found that it isn't always the best model to describe every behaviour. So the question is, explain what is meant by validated evidence. So to answer this, you don't actually have to refer to anything to do with the wave model. It's what is meant by validated evidence. Well, in science we accept it as evidence if there's been a hypothesis that's been tested by an experiment and what is observed in the experiment agrees with what was predicted by the hypothesis. So that's evidence. So there's 2 marks available. So if you refer to the fact that the results of an experiment have supported a hypothesis, and that the results of that experiment have been confirmed consistently when the experiment has been repeated. Part C tells you the threshold frequency of lithium and asks you to find the work function. So let's jot down the equation again. HF equals phi plus EK max. And let's think what we know. If the frequency is too small, so the HF is less than the work function, the photoelectric effect won't happen. If F is very big, so that HF is much more than the work function, then the electrons are emitted and there's energy left over, which is kinetic energy. The borderline case, the special frequency, is when HF is just equal to the work function, and at that point the photons have just got enough energy to provide the electrons with the energy they need to escape from the surface. Well, that much energy is called the work function, and that special frequency is called the threshold frequency. So at the special frequency, threshold frequency, and we usually show it's the threshold frequency by putting a little note after it. At the threshold frequency, HF is just equal to the work function, and there's nothing left over, so EK max is 0, so that's why we miss it out. So the work function is HF, so 6.63 times 10 to the minus 34 times the threshold frequency, which we've just been told, 5.5 times 10 to the 14, which equals 3.65 times 10 to the minus 19 joules. And for the last part, calculate the maximum kinetic energy of the emitted electrons when light of frequency 6.2 times 10 to the 14 Hz is incident on the surface of a sample of lithium. So this is just simply a case of using the equation. HF, that's the energy which the photons bring in, equals phi, that's the work function, the energy the electrons need to get off the surface. And what's left over? Well, what's left over will be the maximum kinetic energy. Maximum kinetic energy, remember, because phi is the energy you need to get the electrons off the surface, which are easiest to get off. Some are more difficult to get off. They need more energy than that, so they have less kinetic energy. So rearrange the equation. EK max equals HF minus phi we've already worked out what phi is, the next previous part, and that gives us an answer of 4.6 times 10 to the minus 20 joules.